By November 2025, interstellar comet 3IATLAS had already been examined by more instruments from more vantage points than almost any comet in the history of astronomy. And it kept doing something that, on paper, sounds like exactly the kind of thing that fuels wild speculation, growing a tail that pointed the wrong way, toward the sun instead of away from it, while astronomers simultaneously debated whether the object was accelerating along its path in ways gravity alone couldn't fully explain. Tom Statler, NASA's lead scientist for solar system small bodies, described the sheer scale of the effort required just to track this single object as something like a stadium full of people all trying to photograph the same baseball in flight, each one holding a different kind of camera from a completely different seat. At least 20 separate instruments spread across Earth, Mars' orbit, and deep space all turned toward the same small, ancient piece of ice at the same time. This is the real story of what actually happened as 3IATLAS got stranger throughout late 2025 and into 2026, why an anti-tail and unconfirmed non-gravitational forces sound far more mysterious than they actually are, and what the largest coordinated observation campaign ever mounted for an interstellar object actually revealed once the data came in. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now because we're just getting started. To understand why this comet generated such an extraordinary level of coordinated scientific attention, you first have to appreciate just how rare an opportunity it represented. 3IATLAS was discovered on July the 1st, 2025, by the NASA-funded ATLAS survey, the Asteroid Terrestrial Impact Last Alert System, at its station in Rio Hurtado, Chile. When astronomers traced its trajectory backward, the math was unambiguous. This object had arrived from outside our solar system entirely, following a hyperbolic path with an eccentricity greater than 6. A number so far beyond the value of 1 that marks the boundary between a bound, elliptical orbit and a truly unbound one-way trajectory that there was no meaningful ambiguity about its interstellar origin. It became only the third such object ever confirmed in the history of human astronomy, after 1I Oumuamua in 2017 and 2I Borisov in 2019. Once that confirmation came through, working backward through earlier survey images, astronomers found pre-recovery observations of the comet dating back to May 7, 2025, nearly 2 months before its official discovery. Images that had captured the object without anyone yet realizing what they were looking at. What happened next was, by any reasonable measure, an unprecedented mobilization of scientific resources. Tom Statler, NASA's lead scientist for solar system small bodies, framed the fundamental value of an object like this directly at a November 2025 press conference. Any object discovered from outside our own solar system, he explained, represents a genuinely new piece of the puzzle in understanding how planetary systems form and develop elsewhere in the galaxy. He described these interstellar visitors using a phrase worth remembering, calling them frozen fossils. Physical relics, preserving a chemical and physical record of conditions from an entirely different star system delivered to our doorstep for a few brief months before disappearing forever. The comet made its closest approach to the Sun, called perihelion, on October 29, 2025, at a distance of roughly 1.4 astronomical units, just inside the orbit of Mars. For weeks surrounding that closest approach, the comet sat too close to the Sun's glare for most Earth-based and Earth-orbiting telescopes to safely observe. But 3IATLAS happened to pass almost directly through the plane of our solar system during exactly this window, which meant spacecraft already stationed at Mars had an extraordinary front-row vantage point that nothing on or near Earth could match. NASA's Mars Reconnaissance Orbiter, using its powerful high-rise camera, captured images on October 2nd. The European Space Agency's ExoMars Trace Gas Orbiter photographed the comet between October 1st and 7th, from a distance of just 30 million kilometers, close enough to make out a fuzzy white disk with a hint of a tail. NASA's MAVEN spacecraft, also orbiting Mars, contributed its own observations, described by Shannon Curry of the University of Colorado, Boulder, in genuinely enthusiastic terms is truly incredible. The list of participating instruments kept growing from there. NASA's Parker Solar Probe, already famous for diving closer to the Sun's surface than any spacecraft in history, turned its Whisper imager toward the comet between October 18th and November 5th. Capturing roughly 10 images per day throughout that window. The Europa Clipper mission, on its own long journey toward Jupiter's icy moon, observed the comet on November 6th from about 100 million miles away, gathering 7 continuous hours of data. NASA's TESS mission, normally used to hunt for planets orbiting distant stars, ran a dedicated observation campaign from January 15th through 22nd, 2026, specifically to study the comet's activity and rotation. NASA's Solar and Heliospheric Observatory captured a faint image as the comet skirted past the sun. On November 19, 2025, NASA formally released the highest resolution images gathered near perihelion, the Mars Reconnaissance Orbiter's high-rise photographs, at a press conference where Nikki Fox, NASA's Associate Administrator for the Science Mission Directorate, remarked with genuine enthusiasm on how prepared the mission teams had been for the encounter and noted that these combined efforts had pushed the agency's science instruments beyond their normal operating capabilities. Fox was also direct about NASA's approach to sharing everything gathered. All of the data, she explained, would be made publicly available, not simply released, but made genuinely usable with the tools needed to actually analyze it, and she extended an open invitation for anyone interested to study the comet alongside NASA's own scientists. Separately, the European Space Agency's own tracking data from the Trace Gas Orbiter delivered a genuinely useful practical result by triangulating observations gathered from Mars against those gathered from Earth. ESA improved the calculated precision of the comet's trajectory by a full factor of 10 compared to previous determinations, a refinement that helped every other observatory aim their own instruments more precisely at the comet in the weeks that followed. Now let's get to the two specific developments that genuinely made this comet stranger throughout this period, because both of them sound, on the surface, exactly like the kind of detail that fuels speculation about something artificial, and both of them turn out to have straightforward, well-understood physical explanations, once you actually look at what real cometary scientists said about them. The first is the anti-tail. As amateur astronomers around the world began tracking 3IATLAS once it emerged from the sun's glare in November 2025, sharp, detailed images began showing something that looks genuinely counterintuitive at first glance. A secondary tail, or in some cases what appeared to be multiple tails, with at least one of them pointing toward the sun rather than away from it, the opposite direction of a comet's usual primary tail. David Jewett, a longtime comet and asteroid researcher at UCLA who has spent his career studying exactly this kind of phenomenon, addressed the finding directly and without any hint of alarm. "It's doing the things comets do," he said plainly. He went on to explain the specific physical mechanism producing this so-called anti-tail. The comet is ejecting dust particles toward the sun, because the day side of the nucleus, the side currently facing the sun and being actively warmed by it, is the hot side, the side where sublimating ice most actively releases trapped dust into space. Jewett explained that these particular dust grains tend to be unusually large, and because larger particles are affected far more slowly by the gentle outward push of solar radiation pressure, the force that eventually sweeps ordinary cometary dust into a tail pointing away from the sun, these larger grains linger for a while in a position that still appears to point sunward, before radiation pressure eventually catches up and redirects them into a more conventional tail. Judging by how far this anti-tail extended, Jewett estimated the dust particles involved were roughly 100 microns across, which he noted is genuinely about 100 times larger than the size most people typically assume cometary dust particles actually are. Amateur astronomers also captured striking images showing what appeared to be several distinct tails branching off the comet simultaneously. Jewett's assessment of the entire phenomenon was consistent and unambiguous. All of these features, he explained, are exactly consistent with a comet nucleus of ordinary or even smaller than ordinary size, simply sublimating in sunlight and blowing dust particles outward in the process. Nothing, he added directly, really shocking there. The second development involves claims of non-gravitational acceleration, and this one deserves a more careful, honest walkthrough because the underlying physics genuinely is interesting, and because the comparison to the first interstellar object ever discovered adds real, legitimate context. Non-gravitational acceleration refers to any deviation in an object's trajectory that can't be fully explained by the gravitational pull of the sun and planets alone. For ordinary comets, this is an extremely common, thoroughly well understood phenomenon caused by the rocket-like recoil effect produced when a comet's own ice sublimates unevenly across its surface, venting gas and dust asymmetrically, in a way that provides a very slight, continuous thrust, nudging the comet's path subtly away from a purely gravitational trajectory. This matters specifically in the context of interstellar objects, because the very first one ever confirmed, 1I Oumuamua, in 2017, displayed genuinely significant, well-documented non-gravitational acceleration, despite showing no visible coma or tail at all, no observable sign of the outgassing that normally explains this kind of effect in ordinary comets. Because astronomers only had a brief, limited window to study Oumuamua before it became too faint to track, they were never able to settle on a fully satisfying explanation for that specific anomaly, and it remains, to this day, one of the genuinely unresolved footnotes in the study of interstellar objects. a footnote that some, including Harvard's Avi Loeb, have pointed to when raising broader questions about that first object's nature. 3IATLAS is a different case entirely, and it's worth being precise about exactly what the current evidence actually shows rather than what speculation has claimed. Dan Green, an astronomer at the Center for Astrophysics, Harvard and Smithsonian, addressed the question of non-gravitational forces directly, telling Sky and Telescope that such forces aren't necessarily present at all in this comet's measured trajectory. Green explained that as more Earth-based positional measurements, what astronomers call astrometry, continued accumulating through November 2025, with the comet now pulling away from the Sun and visible again in the morning sky, researchers would be looking more closely at the genuine possibility of small non-gravitational forces, treating it as an open question requiring more data rather than a settled conclusion either way. Statler, addressing the same question at the same November press conference, gave an equally careful, appropriately hedged answer. The data, he said, do show that there are some changes to the comet's orbit, but he was direct that the uncertainties involved remain fairly large. The core technical obstacle, he explained, comes down to the fact that until astronomers can cleanly resolve the comet's actual solid nucleus, separate from the glowing cloud of gas and dust surrounding it, it remains genuinely difficult to pin down exactly how the object is moving with the kind of precision needed to confidently confirm or rule out a subtle non-gravitational effect. Statler was clear that this specific question was, as of that briefing, being monitored very closely, an honest, ongoing scientific investigation, rather than either a confirmed anomaly or a fully dismissed non-issue. The difficulty in resolving the nucleus connects directly to a third, genuinely unresolved thread running through this entire story. Nobody has yet been able to precisely measure exactly how large 3I-ATLAS's solid, icy core actually is. When the Hubble Space Telescope imaged the comet back in July 2025, it could only establish an upper limit, roughly 8.4 kilometers, about 5.2 miles, in diameter, based on the simple absence of a bright central spike in the image that a larger, more compact nucleus would have produced. Jewett, who conducted that specific Hubble analysis, explained the logic directly. If the comet had a genuinely large nucleus, there would be a visible blip in the middle of the image, and its absence meant the true size had to be smaller than that upper boundary, without actually pinning down the real number. Later, once the comet's geometry relative to Earth improved following perihelion, allowing researchers to better separate the glow of the surrounding coma from any solid material underneath. Updated estimates suggested an effective nucleus diameter closer to 2.6 kilometers, with meaningful uncertainty still attached even to that more refined figure. That specific measurement problem, an object large enough and active enough to be one of the most thoroughly observed comets in history and yet still not definitively measured at its actual physical core, matters beyond simple curiosity. Astronomers were able to determine the mass of the first interstellar object, Oumuamua, reasonably well during its brief visibility window. But the nucleus of the second interstellar object, Borisov, was never successfully resolved by any instrument at all. Successfully pinning down 3I-ATLAS's true nucleus size would give researchers their first genuinely solid comparative data point across all three known interstellar objects, a meaningful contribution to understanding how large these visitors from other star systems actually tend to be. It's worth directly and explicitly addressing the elephant in the room here, because this comet has attracted attention well beyond the usual community of professional astronomers. The Sky and Telescope, reporting on this exact period, noted that even non-astronomer celebrities, including figures like Elon Musk and Kim Kardashian, were being asked for and offering their own opinions about the object, a genuine measure of how far this story had traveled beyond scientific circles. Much of that broader public attention traces back to public commentary from Avi Loeb, the Harvard astrophysicist, who has built part of his career around publicly raising the possibility that unusual interstellar objects might not be entirely natural. It's worth being fair and accurate about this specific point. Raising genuinely testable, falsifiable questions in the scientific literature is a normal, healthy part of how astronomy works, and Loeb has done real, legitimate research alongside his more speculative public commentary. But it's equally important to be accurate about where the broader scientific community has actually landed. Sky and Telescope's own reporting states the consensus directly. Virtually all astronomers see no need to invoke any exotic explanation to account for this comet's actual observed characteristics. Jewett's own blunt assessment that the comet is simply doing the things comets do reflects the working mainstream position of the researchers who have spent months directly studying the real data, not secondhand speculation about it. There's one more genuinely important chemistry story running alongside all of this, and it's worth including here because it represents real, still developing science rather than settled fact. Earlier observations, gathered before perihelion, had already found that 3IATLAS was releasing an unusually high proportion of carbon dioxide relative to water as it vented gas into space, an unusual ratio. By the standards of typical solar system comets, though Jewett has noted that the specific numbers still fell within the broader range of compositions astronomers have measured across various solar system comets, rather than representing something entirely without precedent. As the comet moved past perihelion and researchers anticipated its water production increasing relative to carbon dioxide, the actual chemical evolution of its outgassing became an active, ongoing area of continued observation throughout the following months. Separately, observations using the European Southern Observatory's Very Large Telescope detected the comet emitting cyanide, a molecule commonly found in the comas of many solar system comets. Adding one more data point to the picture, though, again, a genuinely normal cometary signature rather than evidence of anything unusual. So where does this actually leave things, honestly, as this comet continues its permanent departure from our solar system? By August 2026, 3IATLAS had moved into the constellation Gemini, continuing to fade as it retreats from the Sun, still being tracked by observatories around the world using increasingly refined orbital data. Its full observational history has become one of the richest, most thoroughly documented records of any comet in the history of astronomy, precisely because it triggered this unprecedented 20-plus instrument coordinated campaign, spanning Mars orbiters, a solar probe, a Jupiter-bound spacecraft, ground-based telescopes on every continent, and a dedicated exoplanet-hunting satellite, all turned toward a single object during the brief window when it happened to be passing through. Statler's framing of these objects as frozen fossils captures something genuinely true about why all of this mattered so much. Everything this comet's chemistry, its outgassing, its dust, and its trajectory revealed represents a genuine physical sample of material from a star system none of us will ever visit directly, delivered to our own solar system by pure chance, studied intensively for a handful of months, and now heading permanently back out into interstellar space, never to return. It's worth being completely honest about the current state of the two genuinely open threads in this story, because that honesty is exactly what distinguishes real science from manufactured mystery. The precise size of the comet's nucleus remains imprecisely measured, an ongoing target for continued analysis rather than a settled number. And the question of small, non-gravitational forces acting on the comet's trajectory remains, by NASA's own lead scientist's direct account, an area still being monitored closely, with real but still fairly large uncertainties attached to the current data. Neither of these open questions represents evidence of anything artificial or threatening. Both represent exactly the kind of genuine, honest scientific uncertainty that comes from studying an extraordinarily distant, extraordinarily faint object using instruments pushed to the very edge of their capabilities, exactly the kind of uncertainty that responsible researchers describe honestly rather than either dismissing or inflating. So here is where this genuinely, honestly stands, grounded entirely in direct statements from NASA's own scientists and the researchers who have spent months studying this object firsthand. 3IATLAS did get stranger throughout late 2025 and into 2026 in the sense that its behavior kept producing genuinely interesting, sometimes visually startling phenomena, an anti-tail pointing sunward, hints of possible orbital deviation, a nucleus that has resisted precise measurement even under intense scrutiny from more than 20 separate instruments. But every one of those developments, according to the actual scientists who examined the real data, fits comfortably within the well-established, thoroughly understood physics of how comets behave: dust ejection, radiation pressure, outgassing asymmetries, the same basic processes that have explained cometary behavior for generations, now being observed with unprecedented precision on a genuinely rare visitor from beyond our own solar system. That is not manufactured drama built around an exaggerated headline. That is the honest, remarkably thorough, genuinely fascinating record of what the largest coordinated observation campaign ever mounted for an interstellar object actually found, straight from the people who ran it. If this kind of story is what you come here for, one grounded in exactly what NASA's own scientists measured and directly said, rather than exaggeration, hit subscribe and turn on notifications. Because there's clearly more genuine science in the real data than any invented mystery could ever offer. Drop a comment telling me which part of this comet's real behavior surprised you the most, the anti-tail, the trajectory uncertainty, or the sheer scale of the observation campaign itself, and share this with someone who still thinks the strangest thing about this comet is something it was never actually shown to be.